Recording started.
Hi, sc9 students. As you may know, on our last session, the group session that we had, where we had two teams competing, we weren't able to finish it. It took a little longer than I thought it would. So as a result, I'm going to be doing this recording on my own and sending this out as well. So just a reminder that our test is coming up on May 31st. And so if you do both these recordings, if you watch both of them and practice the PDF files until you can get them all the questions on your own, you should do well on the test. Also, for students who were in the session, if you find there were certain questions that you had difficulty with while we were in the session, those are probably good ones to practice and make sure that you know. So I'm going to get started then. And when we did this session before, I played a video that I thought was a really cool video of a pistol shrimp who was actually one of the participants we had in our last session, one of our team members. And unfortunately, I left my mic on, so I'm not going to do that this time, but I want to show you the video again because I just think it's the greatest video. So I'll turn my mic off and I'll put it on in just a sec here. Well, I'll tell you, that is one shrimp that you do not want to mess with. Okay, so guys, what we're going to do at this point is finish off where we left off in the session before. So I'm going to go over to page 18. And page 18, I kind of went into it, but we were going fairly quickly, so I want to just slow things down a little bit so you can understand these concepts a bit better, and we'll go from there. Okay, so let's review what each of the numbers mean in the boxes in the periodic table. And so we can see that those top numbers stand for the atomic number, and the bottom ones stand for the mass number, or the atomic mass number. The atomic number, which is the top one, stands for both the number of protons and the number of electrons, whereas the bottom number stands for the number of protons plus the number of neutrons. The reason it stands for those ones is because the electrons are so tiny compared to protons and neutrons, they basically don't count. So when we're counting the mass of an atom, the atomic mass, we only count protons and neutrons. Okay. So we can see that the atomic number is 24 and the mass number is about 52. It's very, very close. So the only type of particles that are not shown here are the neutrons, because again, this number stands for protons or electrons, but this one stands for protons plus neutrons. So we can calculate the neutrons, and let's see how we do that. If we subtract the atomic mass, which stands for protons plus neutrons, from the atomic number, which stands for just protons, we get the number of neutrons. Okay, so for this element, it would be 52 minus the 24, and that's going to give us 28 neutrons. So let's see how we'll use that information to solve the next question. So this question says an element in the periodic table has the following info in the box. It's got the atomic mass and the atomic number. And which of the following is true? Is it that the number of electrons is 13? Yes, that is true, because the atomic number stands for the number of electrons or protons. So that means this is false, because this should be 13. And what's the number of neutrons? Well, again, that's the atomic mass minus the atomic number, which would be 14, so that's not true. So the only one that is true is the first one. Okay, moving along then. So we talked about what a translator does in real life. They translate from one language to another, and so what we're talking about here, and again, I know I've gone over this, but I just want to take it more slowly. We're talking about going from chemical formulas to chemical words. So here we take each one of these formulas and put them into words, and because we have 2, that's sulfur dioxide, and this 3 tells us we have sulfur trioxide. Okay, and remember, We only use the di and the tri and that sort of things when we have molecular compounds. If we had an ionic compound and there was a 2 here, we wouldn't even use that 2 in helping us tell what the name is. Okay, so moving along, we said then that these are the reactants and these are the products. So sulfur dioxide reacts with oxygen to produce sulfur trioxide. So this whole sentence would come from this formula. But the steps we use are, first of all, we take the chemical formula of each compound, change them into words, and then we use these words to produce a sentence like this. So we could say that this sulfur dioxide reacts with oxygen, or we could say it burns with oxygen, assuming that it actually did burn in the presence of oxygen. Okay, so moving along, this question says, state the following chemical reaction in words. Okay, so we know we have hydrochloric acid and sodium hydroxide as the reactants. So we look for one of the answers that has those two as the reactants, and that's B and D. And so now which one is going to be the right one? Well, we know that water is produced as a product and sodium chloride. So products are water and sodium chlorine. Oops, chlorine, it should be chloride, because the ending of the second compound always has to be IDE. So B is not correct, but D is correct. So again, pay attention in this one to what's listed as the reactants and the products, and that has to match up with what we see here in the equation. Okay, so moving along. This one says, be able to state the number of elements in a compound and the number of atoms of each element. And I pointed out during the session before that there's a mistake here, and I'll tell you what that is when we get to it. So, okay, we need to come up with the number of elements. We see there are 3 elements, carbon, hydrogen, and oxygen. And how many atoms of each element? 2 carbon atoms. There should be 6 hydrogen atoms, and I said 5 here, and 1 oxygen atom. Okay? So, moving on to the question, this compound, we're looking at a different compound here, has how many elements? Again, it has 3, Cu, N, and O. How many Cus? We have 1. How many N's? We have 2, because we have 2 outside the brackets. How many O's? There are 6, because it's 2 multiplied by 3. Okay, so whatever is outside the brackets, we multiply by everything that's inside the brackets. Okay, moving along. We talked about the fact that chemical reactions are sped up by 2 different factors. One is higher temperatures, the other is increasing the amount of surface area. We see both of those things in a barbecue. We see higher temperatures causing the burgers to cook more quickly, and we see increased surface area because we chew up the meat. You know, if you have steak, you grind it up to get hamburger, and so you've got more surface of the meat that's being exposed on the grill. So those 2 factors, again, speed up chemical reactions. So this question is saying which is not an example of a reaction that speeds up as a result of increasing the surface area. If you have coal dust instead of chunks of coal, that is. A log broken into small pieces, that does increase surface area. Crushed ice is going to dissolve better than large ice cubes, but hamburgers cook more quickly when you increase the temperature. That has nothing to do with surface area. Okay, so this is actually the point here where I was wanting to emphasize some things a little bit more. And so, first of all, we look at all matter being divided into 2 different types of matter, mixtures and pure substances. Pure substances can be either elements or compounds. Again, elements are just one kind of substance. Compounds are 2 or more elements, and they're joined together in a chemical reaction. They're like permanently joined together. And so we can see that some examples of elements are H, Fe, and Cu, or, you know, hydrogen, iron, and copper, whereas compounds, some examples are water and sodium chloride. Okay, so again, those are both examples of pure substances. Then we look at mixtures. Mixtures have variable composition. Pure substances have constant composition. So we're looking at heterogeneous and homogeneous mixtures, but we usually look at some other words which are mechanical solutions or mechanical mixtures and solutions. Okay, so these are where we have a mix of two or more substances. And the difference between the two is with a solution, such as salt water, we've got two or more substances put together, but they look like only one substance, even though there's two or more substances. Whereas with a mechanical mixture, they look like two or more substances. You can tell the substances apart. So for instance, if you have sand, it doesn't look like just one thing, it looks like two or more substances. So again, these two things are mixtures as opposed to pure substances. Okay, so now when we come to this question, let's see how we'd solve this. One substance which is composed, well, let's do it this way. We're looking for a solution. What's the definition for a solution? Well, we know that that's when you have two or more substances and they appear like one substance. So that's going to be number 4. Okay, mechanical mixture, we know we have two or more substances again, and this time we can tell the two substances apart. So that's going to be answer number 3. An element we know is made of just one substance, so that's going to be answer 1. And a compound is two or more substances, but they're joined together to form a new substance, so that's going to be number 2. Okay, so again, those are important to know. All right, so this here is an example of a situation where you've got a molecular model and you need to use the information about it to predict something about another molecular model. So here we can see that this is nitrogen, this is fluorine. Okay, so what's the one underneath going to be? Well, we see we have two nitrogens. What do we call it when we have two of something? Dinitrogen. Okay, so far it's either answer C or D. How many fluorines do we have? We've got 4, which is tetra. Tri is 3, 4 is tetra. So it's going to be dinitrogen tetrafluoride. And again, remember the second compound is always changed to IDE. All right. So now we need to look into chemical and physical properties. What's the difference between the two? Well, the key difference between these two is that physical properties have to do with the properties of only one substance, whereas chemical properties relate to how a substance reacts with other substances. So here's an example of a physical property. A diamond could be called hard, and it could be described as shining brightly. So those are both physical properties. Those are things that we see with our eyes or sense, maybe with our touch. So here's some examples of physical property. Color, luster, that has to do with shine. Melting point and boiling point, hardness. Malleability, okay, that has to do with whether you can hammer something into a sheet. Ductility is whether you can pull it into a wire. Crystal shape. Solubility, excuse me, solubility, that's how soluble, how well something dissolves in something else. Density, you know, how dense something is refers to how much mass there is in a certain amount of volume. And conductivity, and that could relate to whether it conducts heat or electricity. Okay, so those are all physical properties. And again, really important to memorize those. With chemical properties, again, they relate to how a substance relates to other substances. And here's some examples, whether something reacts with acids, whether it burns in oxygen. Here's another one, how it behaves in air. So some things might burn in air and some things just might behave differently in air. For instance, they might rust in air. How something reacts with water. And how something reacts in the presence of heat. Now sometimes heat could be more of a physical property. You know, if you heat up an ice cube and it changes into water, that's something physical. But if something actually reacts, if it's a chemical reaction that takes place, that's where heat has to do with a chemical property of matter. Okay, so let's look at this question here. It says, in chemistry we looked at physical and chemical properties. Here are a variety of properties. Which of the following are chemical properties? They're not physical properties. Okay. Let's look at them one at a time. Let's check off the ones that are. Has a specific melting point. That's not chemical, that's physical. Nailable or struck with a hammer, that was one of the ones that was listed on that physical list. Burns in oxygen. Yeah, whenever something relates to another substance, reacts to another substance, that's a chemical property. Ductility, stretching into a wire, no, that's physical. Able to dissolve into another substance, no, that's physical. Because even though it's dissolving, that's not really a chemical reaction. Reacts when exposed to heat, yeah, because it's reacting, it's a chemical property. Reacting with acids, again, a chemical property. So we've got 3, 6, and 7. That's going to be answer C. Okay, on to the next one. Now we're looking at not physical and chemical properties, but physical and chemical changes. A little bit of a difference. So physical changes are when the size of a substance changes, but the substance stays the same. So, for example, if you take some glass, break it into small pieces, those are physical changes. You haven't done anything chemical. Another thing is when you change the state of something. So when we talk about the state of matter, that's like liquid, gas, solid sort of thing. So if we change from liquid to water, or sorry, liquid to gas, that's a physical change because the substance is still water. It's not actually changing chemically. Now, another important thing that I didn't say here, but I could have said, physical changes cannot, or sorry, I should say they can be reversed. Okay? So for example, if you take something and change its state from liquid water to gas, you can change it back from gas to liquid water again. So physical changes can be reversed. Chemical changes. When something new is produced, for instance, if a gas is produced in a reaction, that's something new. If a solid is produced, we call a solid a precipitate when it's produced in a reaction, that's something new that's produced. Okay, chemical changes cannot be reversed. Because something new is being produced, you can't go back to what you had. Okay, so that's a big difference between physical changes and chemical changes. So when we say that something new is produced, it could also be color or odor. So that's something that's really important about chemical changes. Something new is always produced. So what is that something? Well, it could be a new substance, like a gas or a solid precipitate, or it could be a new color or a new odor. But whatever the case, something new is always produced with a chemical change. All right, so here's some physical changes. Again, these are all different states of matter changes. Going from a gas to a liquid, going from a liquid to a solid. Any one of these directions is a physical change. It's a change in the state of matter. Okay, here are some chemical changes. You can see that this penny has reacted with something and it's turned green. Maybe it's rusted. So that's a chemical reaction. Another example of a chemical reaction, okay, so that involved a color change. This involves gas bubbles being produced, such as when you add together baking soda and vinegar. Okay, now let's talk about endothermic and exothermic. So what's the difference? Again, just remember exo has EX in it. If you can remember the word exits, something exits, it leaves something, it's produced by something. So in an exothermic reaction, heat is produced. It exits from the substance. So a combustion reaction is an example of an exothermic reaction because heat is produced. Whereas an endothermic reaction, heat is removed. In other words, it becomes colder. It doesn't become hotter. Just take some vinegar and baking soda, put them in a jar, shake it up, and it will become colder. Okay. So when a reaction involves a chemical change, a new substance is produced. Which of the following would be evidence of a new substance being produced? Well, let's have a look. Bubbles form. Yes, that's going to be a gas, so a new substance is produced. A precipitate is produced. What kind of substance? Well, that's a solid, right? Substances with new properties are formed. Yes. That sounds like a new substance. So any one of those is an example of a new substance being formed. Okay. Next question. Identify which of the following is an example of a physical change rather than a chemical. Okay, physical change, well, that would be a change of state. Because you're not actually changing something chemically. Going from solid water to liquid water is not actually changing, it's still water. Whereas any one of the others, if you have a change of color, odor, or formation of solid or gas, something new is produced, and that's a chemical change. Okay, let's check this one out. A physical change involves a change of size or state. In this type of reaction, nothing new is produced, and the reaction can be reversed. When Sally puts a block of ice into a frying pan, the ice disappears. Okay, let's look at what we have so far. Ice disappears. We must have melting so far, right? Just going to write that down. Melting. But when she holds an ice-filled jar above a pan, water is seen dropping from the cold jar. Okay, so what must happen? First of all, that water, well, first of all, the ice that you had in the frying pan must melt to become water, but that water must eventually become steam. Okay, so we have melting, so then we have from liquid water to steam, that's called evaporation. So we've got a bunch of steam in the air. Now you're holding up some ice, an ice-filled jar, and that steam is going to collect on the outside of it. That's called condensation. The steam that's in the air is going to condense to become liquid water again. So that's condensation. Okay, so again, here's what's taking place. Going from solid ice to liquid water, and you're going from liquid water to steam, evaporation. You're going from steam to liquid, which is condensation. So the order is melting, evaporation, condensation, and that's going to be answer C. Okay, on to the next one. Which of the following statements is not true? Only chemical changes produce a new substance. Well, that is true. Dissolving a substance into another involves a chemical change. No, it doesn't. Dissolving is a physical change. It can be reversed. If you dissolve something, you can get it back again. Okay? Burning a substance involves a chemical change. True. Something new is produced when you burn something, right? Only physical changes can be reversed. That's true. Chemical, you can't. So again, only B is not true. Dissolving is not chemical, it's physical. Okay. So, which of the following situations would involve a chemical change and exothermic? Okay, well, we know some of the properties of chemical change. Something new is always produced. So we're going to look for something new. Just going to write that above there. Exothermic, we know that heat exits or is produced. So, which one of those shows that? Well, heat exits. Which one of these produce heat? This one says heat is added, so it's not produced. This says heat is released as ice freezes. But ice freezing is not a chemical change. That's a change of state. It's a physical change. Combustion reaction, well, we know that is exothermic. Heat exits. It's produced. Gasoline explodes. Yes, that's a chemical change, isn't it? So C is the right answer. And this one is not the right answer because the jar is getting colder. Heat is not being produced. It's being used up. So this is endothermic. Okay. So the answer again for this one is going to be C. Next question. Okay, here we're going to talk about when you are talking about ionic compounds, you see some ionic compounds with Roman numerals in them. What does that mean? Well, let's just think back to the periodic table. If you look on the left side of the periodic table, you'll see in the boxes, you'll see charges like +1, on the right side you'll see elements, for instance, that have a -1 charge in them. But they only have, the elements on the far left or far right have only one charge on them that you can see in the box. But if you look at what's called the transition elements that are found in the middle column of the periodic table, they have 2 or more charges on them. So for instance, if you look up Ru, you'll see on the periodic table that it can be Ru +3 or Ru +4. So if you see a compound name that is ruthenium 3 oxide, it tells us that it's not the Ru +4 that we're interested in, but the Ru +3. That's the one that's reacting with oxygen, because we've got a ruthenium 3 oxide, means that oxygen is the other element. Okay, so we know that we have Ru +3. If we look in the periodic table for oxygen, we see we have O -2. Now we need to figure out what we're going to end up with as a compound. Remember that we always switch the elements. So because the 2 is up above the oxygen, we bring it down below, and it comes after the ruthenium. Same with the +3 that starts with the ruthenium. That now goes with the oxygen, and again it goes down below. That's what we mean by switching elements. That's how we take the ions from the periodic table and find what the actual compound looks like. Okay? So ruthenium 3 oxide looks like this. This is what its formula is. So even though it's ruthenium 3, it's actually the oxygen that ends up with the 3 in the chemical formula. Okay, but again, remember the 3 has to do with the Ru +3 that went into that formula. So let's check out a question that relates to this. So basically we need to take titanium 4 sulfide and find out what that's going to be. Well, remember that sulfide forms S-2 when we look at the periodic table. So titanium 4 is going to look like, do it over here, Ti +4, and then we're going to have sulfur with a -2. And again, remember when we switch the elements in order to come up with the actual chemical formula, we're going to bring down this 2 that's above S, and we're going to put it right here. And in the same way, sorry that doesn't look the best, I should have made it smaller. In the same way, we're going to take that 4 that's above the Ti, and we're going to bring it down here. Okay. Now, you might be tempted to say, well, that's going to be our answer, because the question's saying, well, what's the formula? You might be tempted to say, well, the formula is this one here, answer B. But remember, when you get a chemical formula, it's always got to be in the simplest form, just like a fraction is. So because we have 2 and 4, we're going to divide 2 into both numbers, and so we're going to end up with Ti1 and then S2, and that always becomes shortened to just TiS2. Okay, because when we have Ti1, we ignore the 1. We just make it TiS2. Okay, so the answer for this one would be none of the above. Okay, I think we're done. And this here was just our joke. What do you get when you add these 3 elements together? Barium, cobalt, and nitrogen. And if you look at their the symbols for their elements, you can see that they make bacon. There you go. Okay, guys, I do want to just quickly jump back into a few questions that I didn't feel like I really covered well enough earlier on. So I'll just quickly jump into those, and then we'll be done. Okay, again, I didn't feel like I really did these ones justice when I first explained them during the session before. Identify which statement below is not true about molecular and ionic compounds. Okay, remember from before that molecular compounds are formed by two nonmetals. An ionic are metal plus nonmetal. So the first one is incorrect. It says that two metals are forming a molecular compound. It should be two nonmetals. This one's true. Ionic compound is metal plus nonmetal. This one's true. Molecular compound is formed by these two. Again, if a molecular compound is from two nonmetals, they both come from the right side of the periodic table, which C and O do. An ionic compound, again, we said it's metal plus nonmetal. This metal comes from the left side of the periodic table. This nonmetal comes from the right side. Okay. So again, the one that's not true, this one here. Okay, on to the next one. Again, we looked at how elements are grouped, organized into columns or groups, rows also known as families, and the closer they are beside each other, the more similar their properties are. So we had a question here, and this one I didn't really go into depth before. So the question says, put a 1 if it's low in its ability to conduct electricity, 2 if it's a strong conductor. Okay? So 1 for a poor conductor. Is copper a poor conductor? No. So it's not a 1. Is a nonmetal like chlorine a poor conductor? Yes. So we put a 1. Metals on the right, or substances on the right side of the periodic table, poor conductor? Yes. Anything on the right side is a poor conductor. Metals which are on the left are good conductors. So again, good conductors are a 2. So a metal like sulfur is a 2. And so is something like any other kind of metal that's on the left side of the table. It's also going to be a 2, strong conductor. Okay, so that's where we get that number, 2112, and that's the number we'd write down. All right, just 2 more to go. The periodic table is made of columns of elements known as groups. Which statement is not true about group 1 elements? They are mostly all metals. That's true. I say mostly all because hydrogen is there, so they're mostly all metals. True. Conduct electricity poorly. Not true. Metals are good conductors. Have a charge of +1. Yes, everything in group 1 has a charge of +1. They're reactive substances. That's true. The substances in columns 1 and 2 are both reactive, especially those in column 1. Also, the second last column, second last to the right, on the right side of the periodic table, those are reactive too. So something like chlorine is very reactive. Okay. Last one we're going to go over again. It says calcium, barium, magnesium are found in column 2. So again, we know those are metals. Helium and argon are found in column 18. That's the last column. Those are the inert substances. They're inert because they don't react very well with other substances. So which of the following is not correct? Argon is inert. True. We just said that it was. It's in the last column, 18. Barium is a nonmetal. Well, it's in column 2, so it's got to be a metal. That's not true. Magnesium is a reactive substance. It's in column 2. We said 1 and 2 are reactive, so that's true. Calcium, magnesium, and barium share common properties if they're all in the same column, column 2. They must share common properties. Okay, so only B is not true. All right, so we've now covered all these questions that I wanted to cover. All I can say is please practice them until you can get them all on your own. And if you do that, you should do pretty well on the next test coming up, which is on Monday. So please study hard, guys, and I know you can do well. Take care and have an awesome day.